Alright, we're finally starting our second unit in BC Calculus, and this unit's going to be on sequences and series. The focus is going to be a lot heavier on series, but we need to review or get an understanding of sequences first to actually be able to do series. So, sequence notation first. Generally, sequences are written using a sub n equals, whoops, I'm going to scroll all the way back up here and get a sneak peek as my computer glitches out. Sequences are usually written using a sub n instead of y. And if you see that a sub n notation, it means that your equation or your points are going to be discrete. Remember, it's discrete versus continuous. If you plot a discrete graph, the points are separate. We don't connect the dots. There's nothing in between them. So discrete are their own individual points. And usually for sequences, you'll see something like a sub 1 equals something. And a sub 1 just means the first term in the sequence. And then there's a sub 2 and a sub 3, so on and so forth. But there's nothing in the middle. There isn't a sub 1.5, a sub 2.5, so on and so forth. So when you graph it, you'd have something like this where you have an axis a sub n. Well, now I guess you'd have an axis n where you have 1, 2, 3, 4, 5 like this. And then you would have an axis a sub n where you have the outputs and you graph the outputs. Now, the nice part about sequences is if the outputs follow some sort of pattern, you can treat it like a function. You can create a function that matches it that goes through the points, but just remember that it's actually discrete, so we only plug in those nice integer valued numbers. Okay? Generally, when we're writing values of a sequence, we use these cool braces here, and we write numbers like 1, comma 2, comma 3, comma, and then you'll see ellipses at the end very often just to show that the pattern continues to infinity. We use braces because it's a list as opposed to parentheses, where if I did 1, comma 2, it would be all the numbers in between 1 and 2. If you see braces, it's just those discrete numbers. You can graph sequences as well on just about any graphing calculator. And if you check my website, you'll see that there's actually a handout for how to graph sequences on the TI Inspire. More on that later, though. Alright, let's get to it. It's important to remember how to actually write formulas if you're given a sequence of numbers. For example, if you're given a sequence of numbers that are linear, like -3, -7, -11, how could you fit a function to it if that's a discrete sequence? Well, first off, I always like to go ahead and make a quick chart, a quick table where you have n and then a sub n. Okay, I think we just have 3 values here, so we can do something like this. First value, second value, third value, so on and so forth. And then our first value, our output's -3, then -7, then -11, so on. We're assuming it follows some sort of pattern. Okay, if there's some sort of constant difference you can add or subtract and find a pattern, then it's going to be a polynomial, linear, quadratic, cubic, so on and so forth. Taking a look at this one, it looks like it goes down 4 every time, subtract 4, subtract 4. So there's that common first difference. It tells us it's linear, it's a constant slope. So the first derivative would be -4 in this case. And it lets us set up a function. So we could say a sub n, and I would use that hk form, that m x minus h plus k. In this case, though, instead of x, we're going to be using n, but it doesn't really matter. Our formula for this could look something like a sub n is our slope of -4, n minus, pick any set of points. Maybe I'll pick n minus 1, minus 3, fine. There's your formula. You can always simplify out. Same thing here, we could have said a sub n equals -4, n minus 2, minus 7. It's the same formula. If you expand everything out to put it in slope-intercept form for a function, it still works. A little bit more difficult is if you have to fit a quadratic function to a sequence. And there are really 2 steps here. Okay? We know our quadratic function is going to be that ax squared plus bx plus c, or in this case instead of x I'm using n, which gets a little bit confusing with the an, but realize this is a times n and this is a sub n, and we should be just fine. So 2 steps to it. First thing we want to do is find that y-intercept c, because then we can plug that in. And then from here, all we need to do is use 2 more points, and we'll go ahead and create 2 systems of equations to find a and b. So similar start to before. We have a sequence 2, 7, 18, 35. So we set it up and we say, okay, n and a sub n. I'm going to set this one up a little bit differently because I know I'm looking for the y-intercept. That's like the 0th value. It's the 0th term. We don't start with the 0th term. In sequences, we always start with the first term. So and then we'll go ahead and work backwards. Okay. So we know that the first term was 2, the second term is 7, third is 18, fourth is 35. And in order to work backwards, we need to identify the pattern. In fact, how do we even know this is quadratic? Well, we take a look and we see that we go up 5, and then we go up 11, and then we go up, well, I'm guessing this one's 17. There's no common first difference. There's no constant slope, so we know it's not linear. But if we go down a second level, we see we go up 6, up 6. So I bet we're just going up 6 every time. Or if you work from right to left, we're going down 6 from 17 to 11, down 6 from 11 to 5, which means we would go down 6 from 5 to -1. Which tells us that in this case I went forwards, or I subtracted 1 to get to 2, which means that our y-intercept is 0, 3. 3 minus 1 is 2, plus 5 plus 7, and that keeps that constant second difference. Anytime you have a constant second difference, it's going to be quadratic. Constant third difference, cubic, so on and so forth. So we can see that just by working backwards, our y-intercept in this case is 3. Which is useful because now we know that our equation is a sub n equals a times n squared plus b times n plus 3. There's that y-intercept. If you replace all the n's with 0, you get 3 out. Okay. From here, we're just going to use a couple of the other points that we know to find a and b. For example, we know that a sub 1 is equal to 2. All right, that tells us that in the table. When you plug 1 in, you should get 2 out. So 2 has to be equal to a times 1 squared. When you plug 1 into the equation, you get 2 out. B times 1 plus 3. Or simplifying a bit, it tells us that 2 is equal to A plus B plus 3. Or even a bit more, we know that subtracting 3, -1 equals A plus B. Got that from A sub 1. Then let's go ahead and take a look at A sub 2. A sub 2 tells us when we plug 2 into the equation, we should get 7 out. So 7 has to be equal to a times 2 squared plus b times 2 plus 3. So we get 7 equals, let's see, this is going to be 4a plus 2b plus 3. We can subtract 3 and get 4 equals 4a plus 2b. If you were to stack these two equations on top of each other and solve just using a system of equations, or even solve the first one for a or b, you would be able to figure out a and b and you would get your quadratic equation. But in the interest of time, I'm not going to finish solving. If you want to do this on your own, you should find that the final answer is a sub n equals 3n squared minus 4n plus 3. So you should find -4 for b and 3 for a. Alright, so there's your reminder. So let's move on. You will have to simplify factorials as we go through here, and luckily factorials are fairly easy. Remember, a factorial just takes the largest number and then multiplies it times every whole number down until 1. So times 6 times 5 times 4 times 3 times 2 times 1 over the bottom. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then if you write them out, if you expand them like this, it's pretty easy to see how to simplify. So in 7, 6s, 5s, 4s, 3s, 2s, and 1s all go away. So we really just end up with 1 over 10 times 9 times 8, which isn't too bad. 1 over 10 times 72, which is 1 over 720. Okay. Easily simplified. Don't need a calculator for it. Nothing too bad. Things get a little trickier though when they ask you to simplify a factorial that uses variables instead of numbers, but not too much. 2n plus 1 factorial. Well, that must mean it's 2n plus 2 factorial. It's 2n plus 2, and then 1 smaller would be 2n plus 1. Subtract another one, we get 2n. Then we get 2n minus 1, 2n minus 2, and this continues all the way down until we have times 2 and then times 1. So however large n is, we know it always has to end down at 1, definition of a factorial. And so we can take a look at the bottom. We know this one's going to start with 2n, and I'll line them up, and then we subtract 1 from it, and then subtract 2 from it, and it goes all the way down until 2 and then 1. So we can see just by looking at the pattern that these will all cancel out, and this factorial actually reduces to 2n plus 2 times 2n plus 1. Nothing too bad. The reason that we're going through all these is because in order to solve sequences, a lot of times it's easier to simplify things before you start, and you'll need to do this often with series. Alright, so part 3. One of the big focuses of this unit is trying to figure out if things converge or diverge. And we're going to start with sequences because they're much easier than series. And then we'll try to apply this knowledge to a series. If you want to see if a sequence converges or diverges, ultimately we're just going to be looking at the limit as n gets infinitely large. We want to see if there's a pattern to these numbers. Are they getting closer and closer to a specific number? And it's a little bit difficult to see if you wrote it out like -3, -7, -11, so on and so forth. Are we getting closer to a number? Well, maybe. But I think it's easier if we remember that formula we looked at before, -4 n minus 1 minus 3. If we find the limit of this equation as n gets infinitely large, then we can see if it actually converges to something. So although it might be difficult to look at the individual terms and recognize if they're converging to a specific number, it's much easier if you have an equation. Apply our limit, and we're done. So I have a few examples here. Let's take a peek. First example, if you have the sequence given by 5 minus 1 over n squared, will it converge or diverge? Well, let's take a look at the limit as n gets infinitely large of 5 minus 1 over n squared. Limit properties say that we can take the limit of each individual piece, so it's going to be the limit of 5 minus the limit as n gets infinitely large of 1 over n squared. Well, the limit as n goes to infinity of 5 is just 5, it stays constant. Minus, if you plug in an infinitely large number in the denominator of a fraction, a constant over, it's just going to go to 0. So in this case, it tells us that the sequences, or the terms of this equation, converge to 5 as our n values get infinitely large. A few more. We have the function 5n over the square root of n squared plus 4. We want to know, are we getting somewhere with our terms? So we look at the limit as n gets infinitely large of this function. We can't plug in infinity right away because we would have an infinity over infinity case, and that doesn't really help us. L'Hopital might do something here, but we might as well go ahead and look at another way for solving this. We know that one way as n gets infinitely large is to divide every term in here by the largest exponent. In this case, I see n to the first. So I think we could just divide everything by n to the first. If you take a peek down here, we know we can't distribute a square root, but the square root undoes the square. And so that's really like n to the first as well. So n to the first seems to be that reigning exponent. So let's go ahead and divide everything by n to the first. Here we get 5n divided by n to the first over square root of n squared plus 4 divided by n to the first. We run into an issue with the denominator though, where we can't actually distribute n into the square root because n itself doesn't have a square root. Easy enough to fix though. We know, or we should know, that if we give, let's catch up a bit here, if we give n a square root and a square, the square root of n squared, we know the square root and the square cancel out and leaves us with n. And this function, it can be shown, models the exact same graph as n as we get infinitely large. If we get infinitely small, we need to put a negative there, but we're always interested in infinitely large for sequences, at least at this point, so we can do it like this. Simplifying a bit now, we get the limit as n goes to infinity. 5n over n just becomes 5. We can now rewrite the denominator as the square root over the whole thing. Square root of n squared over n plus 4, square root of n squared over n squared plus 4 over n squared. Simplifying further, the limit as n gets infinitely large of 5 over the square root of 1 plus 4 over n squared. Now we can substitute that infinitely large number in and we'll see that this entire term goes to 0. So we really just end up with 5 over the square root of 1, which is 5. So this is another sequence that also converges to 5. Two more. Cosine of 2 over n. Well, I think plugging in infinity here, we get the cosine of 2 over n. And we might be tempted to think there's no way this would converge to anything, because we know that cosine as a graph just repeats itself over and over and over again. But ultimately what we're doing here is, since we're dividing by n, we're basically turning this number into a constant as we plug in a larger and larger value. The question is, what constant? Well, we know as we plug in a large value of n here, any constant over that goes to 0. So really this is the same function as cosine of 0, and we know cosine of 0 is 1. So this is an example of a trig function that actually converges to a specific value. And it's a pretty cool graph too. If you look at it, it'll actually go up and down and then kind of get smaller and smaller and smaller, but closer and closer to 1 instead of 0. Okay. Last one. Oops, skipping around again. Oh, stop that. So we have a sub n equals e to the 2n over n. We want to see if this converges. So we look at the limit as n goes to infinity of e to the 2n over n. We can't plug in infinity. We'd get an infinity over infinity case. And we can't really even simplify here. So at this point in time, L'Hopital's rule might be a nice one. We do have an indeterminate form, infinity over infinity. So that says we can take the derivative of each. Taking the derivative, we find that e to the 2n becomes 2e to the 2n over 1. Now if we plug in infinity, there's no indeterminate form. We know what's going to happen. We have something that's infinitely large on the top divided by 1, so we get an infinitely large number. In this case, our sequence doesn't converge, our sequence diverges. If it ever goes to infinity, think about the graph. It means the graph is getting infinitely large. It's not approaching a point. Ultimately, what we did on the first 3 examples is we found horizontal asymptotes. We saw that the cosine was approaching 1 here, and so on and so forth. We're finding that asymptote that the graph is getting closer and closer to. This graph has no asymptote, therefore it diverges. The terms don't get closer and closer to a number. Alright, let's finish up. There are some more gnarly sequences that if you try to take the limit of them, life gets a little bit more confusing. One of those cases is a sequence where you have negative 1 to the nth power. And all the negative 1 to the nth power is going to do is every time n is a positive number like 1 or 3 or 5, it's going to keep the negative number there. It's going to make your answer negative. However, if n is a positive number like 2 or 4 or 6, it's going to make the answer positive. And if you think about the graph of that, what happens is it really just jumps up and down. So if you have these even and odd numbers, 1, 2, 3, 4, 5, 6, when n is 1, there's going to be a point down here, and then 2 it's going to jump up, and 3 it's going to be here, and 4 and 5 and 6, and it's just jumping back and forth and back and forth. And it's our hope that they're jumping back and forth and back and forth and getting closer and closer to some number. Well, what we can actually do in this case is we can use what's called the absolute value theorem of convergence, which means if we look at the absolute value of this sequence formula and it converges to something, then the sequence converges to that same thing. But it's very, very specific. If we take the absolute value of n and we look at the limit as n gets infinitely large, if that converges to 0, then, or therefore, we can say that a sub n also converges to 0. However, if we take the limit as, scroll down a bit here, as n gets infinitely large of the absolute value of a sequence, and it converges to some other number that's not 0, so it does converge, but it converges to 1 or 6 or negative 4, then we know absolutely nothing about a sub n. It doesn't tell us if it converges or not. So we only know, yes, if this happens it converges, or it doesn't converge. Okay, so let's take a look at these 2 examples here that I've prepared. We're going to go ahead and take the limit as n gets infinitely large of the absolute value of this first equation. Okay, well, the absolute value of negative just is going to go away. It's just positive 1. So really we're just looking at the limit of n over n plus 1, which is the limit as n goes to infinity. We can do n over n divided by that largest exponent again. which becomes the limit as n goes to infinity of 1 over 1 plus 1 over n. Plugging in an infinitely large thing will make a term go to 0, and we get 1. So the question you have to ask is, when you took the limit as n went to infinity of the absolute value of the sequence, did it converge to 0? No, it didn't. It converged to 1. It doesn't tell if the sequence converges. It tells us nothing. We're done. We're sad. Versus if we take the limit of the second one, so we'll take the limit of the absolute value of the second equation, so the absolute value of negative 1 to the n, 1 over n plus 1. Okay. Well, this will go ahead and this will turn this piece into just a positive 1. So really we're just looking at the limit as n goes to infinity of 1 over n plus 1. Divide by the largest term again, n over n plus 1 over n, which becomes, oops, bad limit notation, sorry, n goes to infinity. So it equals the limit as n goes to infinity of 1 over 1 plus 1 over n. And if you plug in something infinitely large, you get 0 over 1 plus 0, which is 0. Therefore, because this absolute value converged to 0, then we can say that this sequence also converges to 0. So it's pretty powerful. If it converges to 0, it tells us that this alternating sequence, this negative then positive then negative then positive, also converges to 0. Doesn't converge to 0, tells us nothing. Okay, a few more pieces. Monotonic sequences and functions. If something's mono, like mono sound, mono in general, monotonous, hopefully not like this presentation, it means it's the same. And in this case, monotonic sequences and functions are sequences that are either strictly increasing or strictly decreasing. They're either getting bigger all the way or smaller all the way. So for example, if you look at the function f of x equals 2x plus 3, this is monotonic because, well, this is a straight line. Is it increasing or decreasing? It's got a positive slope there. I think if we picture the graph y-intercept to 3, it goes like this. It's going up all the way. It's increasing. Or another way to think of it is that it has a positive slope everywhere. So really, if you wanted to see if it's monotonic, take a look at the derivative. The derivative at this point is just 2. That's a positive number, which means it's increasing. So it's monotonic and increasing. G of x, negative x cubed. That one's a little bit different because we don't know the slope. But if you take a peek at its derivative, that's negative 3x squared. The graph of negative 3x squared is this parabola right here. And that parabola is negative everywhere or 0, and that's okay. And that tells us that the slope of this graph is negative everywhere or at least flat. So this is going to be a graph that's decreasing everywhere, or at least it stays constant. And for it to be monotonic, it can stay constant. So this would be an example of a function that's monotonic, and it is decreasing everywhere. All right. One last piece to note. If you're trying to figure out if a sequence is converging or diverging, a lot of times you get a formula that's in the form of a times r to the n minus 1. And this is exponential growth or decay. And it's going to be growth if r, which is our growth rate, is greater than 1. And it's going to be decay if that value of r is in between 0 and 1. It should also make sense just by the name that if it's exponential growth, it's growing without bound. So therefore, if it's growth, the sequence will automatically diverge. However, if r is between 0 and 1, then it's decaying. It will decay down to some number. There will be a horizontal asymptote, which means that in this case, the sequence absolutely converges. So you'll get a few of these in this form where r will be some number. It may be like 2 times 2/3 to the n minus 1. And if you get that, you immediately know this sequence converges. Our value of r is between 0 and 1. We're good to go. So I hope this helps you get through the first section, 9.1. If you have any questions, as always, send me an email, and thanks for listening.